Welcome to Calc Chats 44. Today we're going to be talking about parametric equations. So first we have to talk about what is a parametric equation. And we've been dealing with mostly functions in terms of x and y. So f of x equals y. We plug in an x. We get out a value for y. So if I plugged in 2 for my function, I might get out, let's say, 7. For my x and y values. And with parametric equations, we're still dealing with x and y values, but we have this new parameter t. So instead of plugging in an x and getting out a y, I'm plugging in a t and getting out 2 separate x's and y's. And so I've kind of put this example, here's just a basic example of a possible parametric equation. So x of t equals t minus 2. And y of t equals t plus 1. And so let's say I wanted t to equal, let's say 6. So I would plug in 6 for my t's. So my x value at 6 would be 6 minus 2, which is 4. And my y value would be 6 plus 1, which is 7. And so we're still getting that x and y plane. But with parametric equations, we might not always have a function that passes the vertical line test. So we could have circles, we could have parabolic shapes. So they aren't necessarily functions in terms of x and y, but they are still only in terms of x and y. We're not adding a third dimension. So we can do a lot of things with parametric equations, just like we have done with normal functions. We can differentiate them, and if we wanted to get, let's say, the derivative of y with respect to x, all we need to do is take the derivative of both parametric equations and take dy dt over dx dt, and that will get us the derivative in terms of the derivative of y, in terms of x. So here we're given x equals t squared minus 5 and y equals 2 sine of t. And if we wanted to find the derivative, again, all we would need to do is take the derivative of each of these separately and then put the y's over the x's. So our dy dt, derivative of y with respect to t, the derivative of 2 cosine t is just, the derivative of 2 sine of t is just 2 cosine of t. And the derivative, the x dt of t squared minus 5 is just 2t. And so if I wanted to find this derivative, I would take, I'm going to use a different color. So dy dx equals 2 cosine t over 2t, or just cosine of t over t. So one of the biggest differences with parametric equations and finding the derivative is that when we find the second derivative, we actually find it a little bit differently. And so this definition may confuse you a little bit, but basically the idea is when we find the second derivative of a parametric equation, we need to kind of separate it. And so we need to find, again, separately, the derivative of y with respect to t. And then we take that over the original derivative of x with respect to t. And so we already found the derivative of y with respect to x. And so in order to find the second derivative, we're going to take our first derivative, we're going to find the derivative of that, and then that will be our top section. And I know I just said the word derivative a million times, but this is kind of going to hopefully become a little clearer as we go through this process. So to find, like I said, the second derivative, first I need to take the derivative of my dy dx. And I'm sorry, I just kind of skipped through. This is the same example that we used from the problem before. And so the derivative of cosine of t over t, we need to use our quotient rule. So low d high minus high d low. So t times negative sine of t minus high cosine t, derivative of low is just 1 over low squared. So that is my derivative of y, derivative of the derivative of y with respect to t, over the derivative of my original x, so t squared minus 5. And this derivative, if we remember, was just 2t. And so then I can kind of try to simplify this a little bit. So I'm just going to leave this as negative t sine of t minus cosine of t. And then I'm going to kind of move this 2t up by multiplying by 1 over 2t. And so that just becomes 2t cubed. So this is my second derivative of my parametric equation. So again, I have to find the first derivative first, take that derivative of again, and then take the derivative of my original x. And then that is my second derivative of my parametric equation. So the last big thing with parametric equations is how to find the arc length of a parametrized curve. I don't know why that was so hard to say. So it's really similar to the formula that we've already discussed for regular functions, except instead of 1 plus dy dx squared, this is just the square root of, we just take the derivative of both of our, both parts of our parametric equation separately, and then we square root that and take that integral. Oops, and this should say dt with respect to t on our interval. And so I'm just kind of going to go through this example really quick because we've already had a little bit of experience with arc length. And so we want to find, first we're given that x is equal to cosine of t cubed and y is equal to sine of t cubed, and we're looking from 0 to 2 pi. And so first we need to find the derivatives of dx dt and dy dt separately. And so dx dt, we need to use chain rule. So we take 3 cosine squared t times the derivative of cosine, and then our dy dt, same idea, sine squared t times cosine of t. All right, and so these are our two derivatives, and then we can plug them into our handy dandy formula. So we're going from 0 to 2 pi of the square root 3 cosine cubed, or not cubed, squared, 3 cosine squared t times negative sine t, all that squared, plus 3 sine squared t times cosine t, and all of that squared. And then we're taking the integral with respect to t. And so I'm not going to go through all of this and solve. You can try to if you want by yourself, but what you're going to end up really taking the integral of, you should end up taking the integral of the square root of 9 cosine t sine squared t. And so we're really taking the integral of 3 times the absolute value of cosine t sine t from 0 to 2 pi, and that should end you up with 6. So yes, this is kind of arc length of a parametric curve. It's, again, very similar to what we've already talked about with regular curves. So now, using our parametric equations, we're going to discuss really quickly the idea of vectors. And vectors are basically these ordered pairs of real numbers, and they help us define magnitude and direction. So in our normal coordinate plane, we have a point x comma y, and it's just kind of a point sitting there. It's not really telling us much other than where it is located. So a point kind of tells us location. A vector tells us kind of how far this point is from the origin and kind of where it is going towards. And so vectors we denote with arrows generally. And so while this point would be the point xy, when we would draw a line or an arrow, that would denote our vector xy. And so vectors are similar to parametrics in that there's usually another variable, another parameter. At least what we're going to be doing with vectors, so there'll be another parameter. But when we're dealing with vectors, they are split into two parts. When we found the derivative of our parametric equations, that we could find the, dy dx, but here we're going to mostly keep our vectors split up into the x and the y coordinates. So here we have some important kind of vectors to note. The position vector, we just denote kind of like our parametric equation, x of t comma y of t, and notice these kind of bracketish arrows around these values. This denotes that it is a vector and not a parametric equation. So you'll see the vectors with those two kind of triangular brackets. Our velocity vector, v of t, we take both of the derivatives separately, and same with the acceleration vector, we take both of those separately as well. So with parametric, when we took the second derivative, we had to do that weird thing with taking the derivative of y over the derivative of x. But here we're just dealing with dx dt, dy dt, and then the second derivative of both of those separately. All right, so here I'm asked to find the acceleration and velocity vectors of a particle, and we're given its position vector is 4 sine of t and 2 cosine of t. And so for our velocity vector, just taking the derivative of those two separately. So our velocity vector should be 4 cosine of t, and our, that's our x component, and then our y component will be negative 2 sine of t. Now our acceleration vector, we needed the velocity to find the acceleration vector, and we're just going to take the second derivative. And so the derivative of 4 cosine of t gives me negative 4 sine of t, and the derivative of negative sine of t gives me negative 2 cosine of t. And if I wanted to find it at a specific point of t, all I would need to do is plug in values, and I would get a vector. And again, when we're dealing with vectors, we do always have two components. We never have one part or one number for our answer. It will always be two different numbers. So here's a really quick example for finding displacement. So we're asked to find the displacement of a particle. We're given its velocity vector is t minus 3 pi cosine pi of t, and then 2t minus pi sine pi of t. And we're also given that at t equals 0, the particle is at 1 comma 5. And so in order to find our displacement, we need to first find the integral from 0. We're asked to find the position of the particle at t equals 4. I was getting ahead of myself. So we need to find position at t equals 4. We are going to use displacement. Sorry, that's my bad. Pretend that's not there. So we're asked to find the position at t equals 4. So obviously we're going to use the displacement. So we're going to write out two separate integrals. So we need to go from 0 to 4 of our x part of our vector. So t minus 3 pi cosine of pi t dt, and then my y part of my vector dt. And so I find, I'm not going to integrate these. You guys are more than welcome to if you'd like, but we find that the displacement has been, for the x-coordinate 8, for the y-coordinate 16, but we are given that the particle starts at 1, 5, and so I need to add 1 to my x value and 5 to my y value to get 9 and 21, and that is my final position of my vector at t equals 4. So this is kind of a lot of what we've already learned, just in a slightly different context. Instead of regular functions, we're using parametric and vectors. And I know this was a lot of information, so please make sure to write down any questions that you have about parametrics and polars, and then come to class with those questions, and we'll get those answered before we head on to spring break. Thank you guys for watching. Please make sure that you like and subscribe.